Great. Do you have any questions? It's okay if you don't.
I'm just going over the significant numbers or significant figures.
Okay.
I guess one question that I did have is, so if you have a number with 3 significant figures and a number with 4, and you're working together with them, you go with 3 because there's less?
Depends on the operation.
It depends on the operation.
If you're multiplying or dividing, then you go with 3.
Okay.
But if you're subtracting or adding, it depends on what the 3 is and what the 4 is. Let me show you what I mean, okay?
Okay.
So when dealing with significant figures for multiplication and division, you go with number of zig figs. So I'm going to write that out. So hopefully you can see my piece of paper here.
Yes, I can.
Excellent. And we have a multiplication division. And here you go with the fewest number of significant figures. And that's a summary of it. So if you have 1.24 times 5.6213, you're going to go with 3 zig figs. And that's the easiest rule to deal with. And that's because this has 3 zig figs, this has 5, so you go with 3 for your answer. You okay with that?
Yeah.
Subtraction and addition, you go with the least precision. So let's look at a number where I say you got A, B, C, decimal, D, E, F. A represents some number, whatever you want it to be. B represents some number, whatever you want it to be. Fair enough?
Uh-huh.
A, B, C, D, E, F. We say that the C is in the ones place. The D is in the tens place, and the A is in the hundreds place. So if we had 1, 2, 3, that would be 100, 20, 2 tens, and 3, 123. And in fact, with the 100, we even say that 100, we don't say 1, 2, 3. The D is the 10th place. The E is the 100th place. And the F is the 1000th place. Now this goes to the left and to the right forever, right? So if we had a number before A, that would be thousands. And before that would be 10,000s and then 100,000s. You with me there? And yes. We could go forever to the right. After F, thousandth, we would have 10,000th, 100,000th, millionth, and so forth and so on. And clearly I'm stopping because I don't know what to say after millionth. I mean, what is that word? I don't know. Okay. When we talk about precision, F is more precise than E, is more precise than D, is more precise than C, is more precise than B, is more precise than A. So the more you know about a number to the right, the more precise it is. So
that makes sense.
If we were to take our numbers and take 1.24 and add it to 5.623, can you see that this one is precise to the hundredths? And instead of saying hundredth, let's say it's precise to two places over from the decimal.
Okay.
And this is precise to 4 places over from the decimal, right?
Right.
This is less precise.
So that determines the sig figs.
That's right. So if we add these two numbers together, I'm going to line them up, and your calculator doesn't do this for you. I think it would be pretty neat for those calculators that have multiple inputs instead of just one line, if it lined things up when you're adding them, because then you could look at the zig figs and say, okay, 4 plus that's 6, 8, 6. So here you can see this is precise to the hundredth, and I can even draw a line there saying that's the end.
Mm-hmm.
And that's where I round. Now, if I'm going to round to that 6, I look to the number to the right. It's a 3, right?
Right.
So do I round up or down?
Down, or it stays a 6.
We actually like to say we round down, and we're rounding the whole number down, because look at the number above, look at the number below. Does that number below look smaller than the one above?
Yeah.
We round it down.
You round it down. Okay.
So rounding down doesn't mean rounding that place down, but rounding the whole number down.
That makes sense.
So there's your answer, 6.86.
Thank you.
You're welcome. All right. Anything else I can help you with?
Not at the moment.
Okay, then I'm going to take off and do some problems beginning where I left off yesterday, okay?
Sounds good.
So we have done yesterday this defined mass number and atomic mass. We did the gold atom has a radius, how many atoms are in there. We learned about writing symbols of isotopes and what isotopes are. Number 8 is another problem that's just like number 6. So we did that one. 10 is actually a problem I assigned in your homework. We talked about the model of the atom by John Dalton versus a Rutherford model. We converted the mass of one oxygen atom into grams. We talked about isotopes and how many protons, neutrons, and electrons are in these silver isotopes. We talked about how you write symbols of isotopes. And for this particular problem, this first one, the second one, and the last one are all correct. This one is not, because when you write the symbol of an isotope, the number on top is the number of things in the nucleus. The number on the bottom is the number of protons in the nucleus. And except for one atom, the number of protons will be less than the number of particles in the nucleus, because the nucleus will have protons and neutrons in it. So here, this says you've got 18 protons in the nucleus, but you only have 9 things in the nucleus. You can't have 18 protons, but only 9 things. So that can't work. The number up top has to be greater than the number at the bottom, except for one atom, hydrogen, which can have a 1-1. The one at the top means one thing in the nucleus. The one at the bottom means one proton in the nucleus. And riddle solved. If you've got one proton in the nucleus and only one thing in the nucleus, there's no neutrons. Okay, so this one does not work. We looked at this one here. This is the atomic weight of strontium. So that's the mass of your average strontium atom, 87.62 AMU. For these isotopes, this number at the top is the number of particles in the nucleus, but since each particle weighs 1.00, that's also the mass. So if you have 88 particles in the nucleus, it weighs 88.0 AMU. If you have 87 particles in the nucleus, it weighs 87.0 AMU. If you have 86 particles in the nucleus, it weighs, your turn.
86 AMU, 0.0.
That's right. So here, if the atomic weight is 87.62, which is clearly closer to 88, there are more 88s than 87s or 86s. That's how you get such a large average. So here, when we talk about the average mass, we don't say, oh, there's one of these, one of these, and one of these. There may be 70 of these and 15 of these and 15 of these out of 100. You with me?
Yes.
And this reflects that difference. This is going to be closer usually to the isotope that there's more of.
And this is talking, this is kind of referring to the intensity, that those are different intensities.
Correct. So this might be an intensity of 100, an intensity of 15, and an intensity of 15. So this is the most common isotope. Here, if you haven't seen this yet, you want to go through and see the videos from yesterday where I calculate the atomic weight of an element based on its isotopes, their masses, and their percentages. And we also did this where we did this for an element with 2 isotopes. We actually calculate the percentage of each. And I didn't go through the whole problem. I kind of set it up and let people do it. So that's where we left off. And now we're going to go ahead and jump into the next part of the chapter where we talk about the periodic table. So are you ready to learn something about the periodic table?
Yes.
Okay, so we're going to draw a periodic table. And there are some things about the periodic table you want to know. And here is a periodic table. And forget about these little lines at the top. But can you see that you basically have this tower of elements here? It's 2 elements wide. You got this tower of elements here that's 6 elements wide. And you've got this kind of box of elements right here. I call that a tower, and a wall, like from a castle. You know how castles always have towers at the edges?
Right.
And then you have the castle wall that's lower. And you see these elements down here? I call that the moat. So let's draw a castle and its moat, shall we?
So there's a specific reason that they're like that? Is that what you're?
Absolutely. And we're going to be learning about that in just a moment.
Okay.
So here's one of the towers. And I'm going to go ahead and write 1, 2, 3, 4, 5, 6, 7. Because if you think of this as being like a tower, there's 7 stories. And just to keep track, I'm going to do this. So can you see this is a 7-story building?
Yes.
Or a 7-story tower?
Yes.
Now the wall actually starts here, and there's only 4 stories of the wall. I'm not going to bother drawing the lines in because I don't need them. The other tower is like this part of the tower. It's like 6 stories tall, but instead of just 2 wide, it's 6 wide. And then the very last end of that tower, you got 1 element up there like that. And then at the bottom, you've got this. Now, you want to know this about the periodic table. This is 2 elements wide, this tower. And when I say 2 elements, I mean 2 blocks. Are you with me there?
Yes.
Okay, and this is going to be 6 elements wide. This is 10 elements wide. And this is 14. Okay, so that's the beginning. Now let's look at more detail that you should know. And when I say should know, I don't mean you should know it right now, but you should learn. So what
All
you
right.
should learn is a column of elements is called a group. This group right here, the very first one is called group 1A. So I'm actually going to put group 1A above it. And lucky for us, the group next to it is called 2A. 1A, 2A. And that's your first tower. The wall we're going to skip. And we're going to go over to the other tower. And the other tower starts here at 3A. And then it goes all the way to 8A at the end. So you got to kind of space it right, but it goes 3A, 4A, 5A, 6A, 7A. Each of those columns is an A. Now the wall are the B's. And the interesting thing about the B's is that they're weird. So if we look at the first B, it's actually 3B. It goes like 3B, 4B, 5B, 6B, 7B, 8B, 8B, 8B. I'm not stuttering. There's 3 8Bs. And then it goes to 1A, 2A. So we don't learn the B's. We just learn the A's because they're as easy as 1, 2, 3. So you want to know all of those groups, 1A, 2A, 3A. You also want to know the periods. So the first row is period 1. The second one is period 2. The third is period 3. You can tell there's only 2 elements in period 1. And in period 3, there's 6 here plus 2 here for 8. And in period 3, there's also 8. Now, here's a really interesting thing, Gabe.
So 1A and 8A are both period 1. Is that right?
No. 1A is this whole thing right here. So 1A is a column.
Right. Okay.
Everything in that column is group 1A.
So their period 1 is within group 1A?
No, period 1 is a row. So
Okay.
this is period 1. It goes, so periods go across, groups go up and down,
Right.
and they intersect. So you can
I guess
have
what I'm trying to do is
something-
I'm trying to get the orientation right. Is in period 1 is 1A the top of that in period 1 and also 8A?
That's right. So there are
Okay.
only 2 elements in period 1. One of them is one of them is in 1A, one is in 8A.
Okay, yeah. And then in period 2, there's 1, 2,
8.
8.
And you've got an element in 1A period 2, 2A period 2, 3A period 2, 4A period 2, and so forth and so on.
Okay.
So it's almost like an address, with a street and a street address. So the street
a
name
street and a number.
and the number.
Okay.
You can think of the period, since it's really long, as being like the street, and the 1A being the number on the address. Okay,
I got it.
cool. Now, the interesting thing here is this part of the moat. You might think it's 1, 2, 3, 4, 5, 6, 7, 8, 9, but it's not. This is part of 6 and this is part of 7. So let's learn a little bit more about the periodic table. And I'll show you why this is part of 6 and part of 7.
The periods, is it?
Yeah, why this is part of period 6 and why this is part of period 7. So I'm going to change my view here so that you can see my web browser. And I'm going to go here to periodic table. Image. And here you can see a number of periodic tables. I'm going to pick one that hopefully is simple. There's a simple one. And I'm going to see if I like this one. I'm thinking I don't like this one. I'm going to go back to the images. Yeah, I don't like this one. I don't like that one. I don't like that one. I like this one.
What are you looking for?
I'll show you in just a moment. So we're going to take a look at this periodic table. Come on. Timeout. The internet just gave me a timeout. Was I behaving badly?
It's because you're teaching your students how to play craps.
Oh, yes, you were there for that one, huh? Okay, this one will do. Ducksters. Okay, I like this periodic table because it's very simple. Can you recognize the two towers, the wall and the moat here?
Yes.
Okay, so if you look at period 1, the numbers at the top of the elements are 1 and 2 in that order, right?
Right.
If you go down to period 3, you'll see it continues 3, 4, 5, 6, 7, 8, 9, 10. Let's jump to period 6. Do you see how it says 55, 56, 57? And then
yes.
what happens?
Skips to 72. So that's where it draws down to the.
But it doesn't skip to 72. It just looks like it skips to 72.
It's just some weird configuration.
Let me show you what this would look like if we put 58 right after 57 where it belongs, okay? So I'm going to type expanded periodic table. And we're going to be looking at images. So here is an image of the expanded periodic. Oh, I don't like that one. Bad choice. This one is fine right here. Oh, this one is fine right here. So they call this extended periodic table. Take a look at that. So here, I'll try to make this a little larger. So here we go from 57, 58, 59. It goes in order. Do you see that?
Yeah.
So do you see how we have taken the pink elements minus the lanthanum and actinium? We've taken these pink elements, which are the moat, and we put them where they belong and shoved everything else over. That's the expanded periodic table. So that's where those elements really belong. And the reason we don't draw this periodic table this way is for a couple of reasons. One reason is that it doesn't fit on an 8.5 by 11 sheet of paper very well. You know, it only uses half of the page and you got half of it empty. Whereas the other one fits it really well, right? The other reason is that these elements here, the pink ones, except for lanthanum and actinium, we don't really use them in chemistry that much for most of chemistry. You know, there is plutonium and uranium in here, but you know, the people that use those are nuclear scientists, right?
Mm-hmm.
So we kind of set them below because, you know, we don't really run into them too often in chemistry. So we kind of put them off to the side. Whereas these ones here in the wall, we run into a lot of these all the time. Like, do we ever run into gold or silver or mercury or nickel or copper or zinc or chromium or, you know, titanium, we do. Those are common, not common, but metals that you can go out and buy. You can go buy gold, it turns out, and platinum. But good luck getting your hands on any uranium. I mean, if you try, you're going to get a knock on your door from some guy wearing sunglasses. And we all know what that means. You are now in an episode of Men in Black.
I thought it meant free lunches.
Yeah, you might get free lunches for the rest of your life. So that's why it's strong.
So that's why those are down there.
Yeah. So they fit down there because it looks good on an 8.5 by 11 sheet of paper. But I want to go back to, away from the jokes here for a minute, and I want to remind you of what I was trying to point out to you. So back to the reality here. What is the first row of the moat part of? What period?
Period 6.
Yep. And the second row?
Period 7.
And we know that because they actually fit in up here, and we can see the numbers as we count across. Fair enough?
Yep.
Okay, good. Now, guess what? We're going to draw the periodic table again, but actually, I'm going to take off from right here. Group 1A and 2A and 7A and 8A, you want to learn their names. So group 1A has a name. They're called the alkali metals, except for hydrogen is not a metal. 2A is called the alkaline earth metals. And these two sound a lot alike. And the way I remember them is I know they're both metals, so I cover that part up, metal and metal. And can you see how group 1A only has one part to its name, alkali? 2A has two parts, alkaline earth. So that helps me to remember the difference between the two. But also, I like to think of it as this way. 1A is like the firstborn and 2A is like the secondborn. And you know how the secondborn are. They always have a chip on their shoulder. They can't live up to the first, born. So this guy, I think of the NE as being representative of the chip on its shoulder. So its name is just a little bit longer than the 1A's because of that chip. Now, maybe you don't have to resort to tricks to remember things, but I do. So I'm just sharing you my tricks.
I definitely do. I liked the 2A. It makes sense, the two words.
Yeah. See, I'm second born, so I've got a chip on my shoulder.
Ah, I see.
Actually, it's not. I am second born, but I don't have a chip on my shoulder because I'm mom's favorite. I was always mom's favorite as soon as I was born. And it's always been that way. And the reason is because my mom was Japanese and I was her only son. So I don't know if you know about Japanese culture, but the males are cherished more than the females.
Yeah.
I was the favorite as soon as I was born, and I didn't have to do a darn thing other than being born. And I would lord that over I'd lord that over my sisters all the time.
Sounds like normal sibling stuff.
Absolutely. Now, 7A are called the halogens, and 8A are called the noble gases. You can probably guess that they're called noble gases because they're gases. The reason they're called noble is because they're rare. So sometimes they're called the rare gases. And they're unreactive. And instead of unreactive, we say inert. So they're sometimes called the rare gases. Sometimes they're called the inert gases. And to help me remember noble, here's what I think. You've got the nobility and you've got the peasant class, right?
Right.
Which is rare, the nobility or the peasants?
Nobility.
They're rare. Now, which one of these don't interact with the others because, they're too good?
Definitely
nobility.
nobility.
So they don't react with the other elements. They're inert and they're rare, noble gases.
Got it.
Okay, now there's more to learn about the periodic table. So we're going to draw it again. Now, what I'm drawing you here is different than what the book does. And the way I'm telling it to you is just to make your life a little bit easier. Okay, so what I'm trying to draw here is beginning at this tower, up here in period 2, group 3A, there's the element boron. And can you see I'm trying to draw the elements that are diagonal to boron going down to the right?
Yep.
We're going to call these the metalloids. And the reason we want to know the metalloids is not because they're interesting, but because they separate the metals from the nonmetals. Now we know copper and nickel are over here, as long as silver and gold. So based on that, which side do you think are the metals, the left or the right?
No, the left.
Definitely. But I'm not going to circle this guy. He's a non-metal. And that's hydrogen. But everything else here to the left is a metal. That includes sodium, lithium, potassium, calcium, things that we don't normally think of as being metals, they are metals. And if you were to have a chunk of pure sodium, you would see it looks like a metal. Everything to the other side, which includes carbon, nitrogen, oxygen, fluorine, things like that, they are non-metals. And that actually makes sense, right? We don't think of carbon as being a metal or oxygen as being a metal. This is going to be important for when we're working with names of compounds. Hugely important. You want to know this. And then I want to take a moment and I want to describe properties of nonmetals and properties of metals. So these are the metals right here. The biggest portion of the elements are metals. But before we move on to, actually, let's do that. Let's do states of the metals or properties of metals, nonmetals, and metalloids. So I'm going to put this off to the side and I'm going to put props because I don't want to spell out properties. I'm too lazy. And I'm going to put metals, nonmetals, and metalloids. And, you know, it's very common for me on a test to ask a question where I say, give me properties of metals, nonmetals, and metalloids. So I'm going to give you the first property of metals. They're solid at room temp. There is one metal that's not a solid at room temp. Do you know which one it is?
Mercury.
That's right. Nonmetals, most are gas at room temp. One is a liquid, and the rest are solid at room temp. For instance, carbon is a solid at room temp. Nitrogen is a gas, oxygen's a gas. The noble gases are time for you to jump in. The noble gases are
What, the noble gases are
they gas, liquid, or solid?
they're gas.
They're gas. We're going to skip metalloids. Metals are malleable and ductile. Malleable means that when you smash them with a hammer, they deform, they don't break. You can break a metal in two with a hammer, but the fact that they're malleable is the reason why you use metals for coins. You know, back when the Romans were around and they were making coins, they'd take a silver plug of a certain mass, and that would be the coin of the day. And to make it more interesting, they would have, they'd place the plug of silver on top of a little relief that might have, you know, a person's head on it, an image of the person's head. And then you strike it with a hammer, and maybe the hammer has an image on it. So you can get images on both sides, but a lot of times you'd only have one image on one side. Now, if you didn't have that plug lined up perfectly with the image, it would be off center. And so that's why so many old Roman coins, when you see them dug up and someone holds them up, the image is a little off center because you're striking it with a hammer. So if you think that's a tough job, though, striking a coin with a hammer, think about the guy who had to hold the coin in place. Man, that's a tough job. Okay, another joke. Nonmetals, if they're a solid, they're brittle. And that is the opposite, of course, of malleable, because here, if they're brittle, when you strike them, they shatter. These guys are conductive. And I'm talking about heat and electricity. And these guys are non-conductive. Now, what I'm showing here also as we move along is I'm showing you how you can figure out the list for one and bounce off of it and get the list for the other. See, I talk about the state at room temp. So what do I talk about here?
The state at room temperature also.
Here I talk about if it's soft or hard. So what do I talk about here?
If it's soft or hard.
Right. And I'm saying soft is malleable and hard is brittle.
Right.
Here I'm talking about conductivity. What do I talk about here?
The conductivity or its lack of.
Yeah. So water solubility, these are tend to be not water soluble. And guess what? Nonmetals tend to be not water soluble.
So they have something in common.
Yeah, they do. And so if you have a substance where you're trying to figure out if it's a metal or a nonmetal, you're not going to throw it in water because it doesn't tell you anything. These guys are shiny and often silvery. These guys, the opposite of shiny would be dull and not silver. Now, are all metals silver? Clearly not. There's copper and there's gold, which their colors are named for their element name, right? Copper is like a color. Another thing we can say about these is that these have high melting points and boiling points. MP means melting point, BP means boiling point. And the reason I say that is because if you have a military background, you know MP is military police. So in our case, we need melting point. And if you work for oil, you know BP is British Petroleum, but for us, it's boiling point. So these guys have relatively high melting points and boiling points, and that's a testament to why they're a solid at room temp. They don't melt until they're a high temp. Now, since these are mostly gases, they tend to have low melting points and boiling points. I mean, let's face it. If you have an element that's a gas at room temp, before it was a gas, it had to be a liquid. Before it was a liquid, it had to be a solid. How do you get the solid to turn into a liquid? You heat it. How do you get the liquid and turn it into a gas? You heat it. So if it's a gas at room temp, that must mean it boiled and melted at a much lower temp than room temp.
Right.
So these are just some of the attributes of metals and nonmetals. Now, what are metalloids? Well, let's take a look just at silicon itself as an example. Silicon is a solid at room temp. It is brittle. If you take a look at a silicon wafer, it will snap apart. Does silicon conduct? Well, it turns out it does so, but very badly. So we don't say it's conductive. We don't say it's non-conductive. We say it's semiconductive.
Semiconductive.
Or in other words, it's a semiconductor. Have you ever heard of that term?
I have.
And that's why it's called a semiconductor. And the really cool thing about silicon is that you can change it by mixing it with phosphorus atoms or with nitrogen atoms, and you can make it more or less conductive. So you can fine tune the conductivity, and that's why people like silicon so much. Now, it's not water soluble. And it tends to be shiny like a metal. And it has a high melting point and boiling point. So which of these properties are like metals?
The shiny, the high boiling point, not soluble in water. I guess the conductivity, I guess, because they're semi-conductive.
Yeah. And which ones are like nonmetals?
The brittle.
Semiconductor and not water soluble.
And
So what I'm trying to point out to you is that metals, some of their properties will, let me back it up.
Metalloids.
Metalloids will sometimes have some of their properties like metals, some like nonmetals, and some in between a metal and a nonmetal. It just depends on the particular metalloid.
And it's just those 6?
Well, these are the 6 most common properties of metals and nonmetals.
I mean, the metalloids on the periodic table are just the 6 that you.
Yeah, just those 6.
Okay.
The book will give you a different list, but we're going to go with my list because the real purpose in my class, the way I teach it, of knowing about the metalloids is that it separates the metals from the nonmetals.
Yeah, that makes sense.
That's our purpose for them.
It helps break down the table to a much more comprehensible stage.
Yeah. So those are the things that I want you to know for now about the periodic table. And so that prepares us to actually answer probably the next few questions. So in groups 4A through 6A, several elements who begin with S, name these elements. I'll just give you the list. There's Si, there's S, there's Se, there's Sn, there's Sb, and I think these are all of the elements in groups 4A, 5A, and 6A that begin with an S. I'm double checking to see if I've missed any. So, what's the name of Si?
Silicon.
Excellent. And you don't want to say silicone because silicone is what you caulk your bathtub with. Silicon is the element.
That's what silicone is made from?
No. So I don't think silicone is really made from silicon. It may be, but
really,
I'm not sure that it is.
Learn something new every day.
The most common form of silicon is sand. Sand is SiO2.
Right.
So that's why I've never looked it up to see what silicone is made out of, but I don't think it's necessarily made out of silicon. It could be, but I'm not sure.
Okay.
Okay, what is the atomic number on silicon?
14.
Excellent. What's the group number?
4A.
Excellent. What is the period?
3.
Excellent. Metal, non-metal, or metalloid?
Metalloid.
Excellent. How about, I'm going to jump down to SB. Do you know what the name of that is?
Antinomy. Antimony.
Close.
Antimony.
Nailed it. What is the atomic number?
51.
Group.
5A.
What is the period?
5.
And what type of element is it? Metal, metalloid, or non-metal?
Metal.
Metal. Now, I think your book calls it a metalloid, but we're going to call it a metal just because it's a lot easier to remember the diagonal. Fair enough?
Yeah, it is. It's green, which is, yeah, like you said, considered a metalloid.
Yeah, but who cares? I mean, honestly, we're not going to be running.
This is your class.
We're not going to be running into any chemistry with antimony. Antimony is that thing you have to pay when you get divorced.
Ah.
Oh, wait, that's
I don't want-
alimony. Never mind. Okay. So,
It's the combination of the feeling and the monetary.
yeah, or maybe this is supposed to be acrimonious. Acrimony. Like that bitter feeling you have. Okay, I'm going to let you fill out the rest of these, but do you have an idea of how to do this one?
Yes.
Then we'll move on. How many elements in the seventh period? Well, remember how I said it helps to know that the towers are 2 wide,
Yes.
that the wall is 10 wide, the other tower is 6 wide,
Mm-hmm.
and the moat is 14 wide. So if we look at our periodic table, how many elements are in the first tower in group 7 or in period 7?
So you're talking about, what was the question again? Just the very first tower?
Yeah, in period 7, how many elements in that first tower?
2.
In period 7, how many elements in the wall?
10.
And in period 7, if we look at this periodic table, how many elements in the second tower?
6.
Yeah, it's filled up. And here, if we look at the moat, how many elements in period 7 there?
14.
14. So we don't need to bother counting, we just add.
Mm-hmm.
6 plus 14 is 20. 20 plus 10 is 30. 30 plus 2 is 32. So period 7, according to the periodic table we're looking at right here, has 32 elements. Now, if we look at our book, let's see how many elements it has. It also has 32. So our book is pretty current. I have used books in the past where they were like 10, 15 years old. And they don't have 32 in the seventh period. The reason I used to use books that were so old is because you could buy used ones on Amazon for like $10. And 95% of the book was the same as the current edition. So what's the point of paying $300 for a book versus 10? The point is save money.
Was the moat smaller?
No. This part, we didn't have this part in the older books.
Okay.
Because these are the ones that have the biggest atomic number. And honestly, most of these here in the second tower of period 7, most of them are things that are so rare that there is no bottle of it sitting anywhere. No bottle of it anywhere. Because someone made two of them, two atoms, and they both disintegrated into smaller pieces in less than a second because they're radioactive and unstable. So I want you to think about that. The guys who are making these atoms here, the atoms that they can't hold on to and they can't put in a jar, what happens to them? They get the Nobel Peace Prize for science. You're in a grocery store, you put two cans on a shelf for 2 years of work, and then they fall apart and break open. What happens? Well, I'm going to tell you, you don't get the Nobel Peace Prize. This is why you want to be a scientist. They celebrate people who can't make anything last. That's just a joke, of course, but it's pretty interesting. Okay, so let's take a look at this. What is the name given to the majority of these elements? Now, this has to be in the context of what we just learned. So we're looking at all these elements right here. In period 7, what is the name given to the majority of these elements? So, well, we could say, well, they're period 7 elements, but that's clearly not what they're asking. But you remember that this is the metalloids. What's to the right of the metalloids?
The non-metals,
And what's to the left?
metals, except for hydrogen.
Except for hydrogen. So there's only one element here, one element in group 7A or in period 7. That's a metalloid. What are the rest of them?
Metals.
Metals. So I think that's what they're asking here. What is the name given to the majority of these elements? They're metals.
Okay.
So what are some well-known properties of these guys?
Solid at room temperature, not water soluble, conductive, shiny, high melting point, high boiling point.
There you go. Okay. Name an element for the following. So non-metal in the second period. There's a whole choice between carbon, nitrogen, oxygen, fluorine, or neon. Lithium is a metal, beryllium's a metal, so they don't work. Boron's a metalloid. So you have your choice of 5 elements. For B, an alkali metal in the 5th period. So is alkali metal 1A or 2A?
I don't know.
It is
Wait.
1A.
You said, yeah, so that's right. That was the groups that you're talking about.
Yeah. We
The
cover
alkali
up
metals.
metal,
That's right.
one
the
part of the
alkali.
name, 1A.
Right.
Now, another way to help you remember alkaline earth is when you think about some of these elements here. Do you see calcium? Calcium is a common element to find in the ground because of sea organisms who make calcium carbonate shells.
Mm-hmm.
And so calcium ends up being part of the earth, if you will.
And it's in the
And it's in 2A.
second group, which is the alkaline earth metals.
Yeah,
That makes
so
sense.
earth. Whereas normally when you look at sodium, you think, oh, you don't think sodium's earth, but calcium may be. But
Potassium.
that's a bit of a stretch, I'm going to be honest with you. Okay, so alkali earth metal in the 5th period, which one was that? Oh, I'm sorry, I said that wrong. Alkali metal in the 5th period.
Rubidium.
Correct. How about the 3rd period halogen? I'm going to tell you, a lot of people would say bromine. A lot of people would say bromine. And bromine is wrong.
Chlorine.
Chlorine. Why is bromine wrong?
Because it's in the 4th period.
It's in the 4th period. It is the 3rd one down, but it's in the 4th period.
Yeah.
An element that is a gas at 20 degrees Celsius and 1 atmosphere of pressure. So here's another interesting thing that you might want to know. It's very helpful. Let's make a list of the elements and what their state is at 20 degrees Celsius, 1 atmosphere. So these elements are liquids at 20 degrees Celsius and 1 atmosphere. So the abbreviation for atmosphere is ATM.
Okay.
So the liquids, the elements that are liquids at basically room temp: mercury and bromine. And that's it. It's a nice list because there's only 2. The gases at 20 degrees Celsius and atmosphere, 1 atmosphere. There's nitrogen, oxygen, fluorine, chlorine, hydrogen, helium, neon, argon. Now I'm going through the noble gases: krypton, xenon, radon, and this OG, which I don't even know what it stands for. I don't even want to try and pronounce it. I'm sure it's some Russian scientist, OG. No, I think it's Swedish. Organism. So here there's 12 elements that are gases at room temp. And according to our periodic table, we have 118 elements. We've just accounted for 14. That means there's 104 solid elements. Now, here's what I like to do for the solids. Here's the liquids, here's the gases, the solids, the rest of them. Because you're not going to find me writing down 104 symbols to make a list. I'm not going to do it. Okay, so the answer to this question is one of these 12. Fair enough?
Fair enough.
Okay. Let's move on then. Now, this is also very interesting. Symbols for 5 elements mix and match a radioactive element. I'm going to pull my little periodic table up here, and I'm going to tell you something interesting. And that is this. Element number 84 is called polonium. It's named after Poland, the country, and it was named after polonium or Poland because the person who discovered it was Polish, and that was Marie Curie, Dr. Marie Curie. She studied radioactivity. And every element, starting with polonium, from there on up, all of their atoms are radioactive. Every one of them, radioactive. So that's
84 and above.
Yep, that's why people are worried about radon in their houses. Because if you have radon in your house, what does it mean? You got radioactive.
There's radioactive material.
Mm-hmm. Now, the reverse is not true. That is to say, if you're below 84, you don't have any radioactivity. In fact, just about every one of these elements has a radioactive isotope. Carbon has a radioactive isotope. It's carbon-14. But clearly, the isotope that dominates is carbon-12 because the mass is very close to 12. And that's not radioactive.
Radioactive means that it emits an X-ray?
No, it means it emits some sort of energy or particle. So radioactive means the nucleus is unstable and it gives off something. It could be a alpha ray. It could be actually we call it alpha radiation, radioactive radiation. It could give off beta radiation, or could give off gamma radiation, or could give off a combination of those two.
Okay.
So here, when we're asked now a radioactive element, we look for one that's bigger than 84, and BK is it. BK does not stand for Burger King. It's berkelium, named after Berkeley, where it was discovered. A liquid at room temp. So what are our two liquids at room temp?
Oh, the two liquids that are two metals that are
Nope, two liquids at room temp.
water.
Elements. One is a metal. What's a metal that's a liquid at room temp?
Mercury.
Mercury. So the other liquid at room temp is bromine.
Okay.
So Br is the answer to B. Which one of these is a metalloid?
Boron.
That's right. Which one's the alkaline earth element?
Barium.
Correct. And how about the group 5A element? By process of elimination, it must be bismuth, right?
Bismuth. Yes.
Okay. So let's continue. There is a model of asparagine in the book. And this is what the model looks like. I'm going to open my book up to that page. Page 108. And hopefully you can see the asparagine here at the bottom of this page. I'm going to zoom in just a little, but I don't want to zoom in too much. Okay, there we go. So that's asparagine right there. And here are the things that you want to know about this particular structure. This structure is called a ball and stick model because the balls are atoms and the sticks are bonds. So do you see where there's a single stick between two atoms?
Yeah, the large gray atoms.
Yeah, that's called a single bond. Do you see where there's two sticks parallel to one another?
Yes.
That's called a double bond. Okay. So this is the ball and stick model. And in the ball and stick model in chemistry, the white atoms are hydrogen. The blue ones are nitrogen. The red ones are oxygen. And these black ones are carbon. Now, do you see the watermark behind the ball and stick model?
Mm-hmm.
That is called the space filling model. Do you see this little red part of the watermark? That corresponds to this red oxygen. This red part of the watermark corresponds to that red oxygen. And this black part of the watermark corresponds to that carbon. Now, in this model, what's interesting, the space filling model, is you don't see the bonds. The bonds are where two atoms touch. That's a bond. So do you see how this is a single bond here and a double bond here?
Yeah.
Can you see how it's a single bond here and it's a double bond here? And the answer is no, you can't, because all you see is them touching. So in the space filling model, you don't know if it's a double bond or a single bond. Fair enough?
Right. You only can see that in the ball and stick model.
That's right.
Okay.
But you can also see it in the structural formula. So with the structural formula, what we're going to be doing is we're going to be drawing the atoms as symbols instead of balls. and we're going to be drawing the bonds as lines. So you see this little oxygen over here? Let me see if I can do this. So we've got an oxygen bonded to a carbon, double bonded to an oxygen. So do you see what this corresponds to over here?
Yes.
And then this goes up to a carbon, which goes to a hydrogen, and then to a nitrogen, which is bonded to 3 hydrogens. So what is this sphere here that I'm pointing to? What does that bond to the lower right?
To a carbon.
Excellent. So we're going to draw a line going down to a carbon. What is that carbon bonded to the upper right?
To another carbon.
Okay, and what is that carbon bonded to the lower right?
Nitrogen.
And what is that nitrogen also bonded to? Upper right and below.
2 hydrogens, or yeah.
That's right. So we're going to put those in. Let's go back to that carbon that the nitrogen's bonded to. What's bonded above it?
An oxygen.
How many bonds?
A double bond.
Excellent. And for that carbon that's below to the left of that one carbon, what's in addition bonded to that carbon that we haven't captured yet?
2 hydrogens.
Excellent.
Single bonds.
So this is called a structural formula. And I think what's nicer about the structural formula than the ball and stick is that we don't have to interpret what the color is. We have the symbol written down.
Mm-hmm.
Fair enough?
Fair enough.
Okay. We'll move on then. So I'm going to put this here so that we can see that this is the answer. I'm also going to zoom back out so that rather than just seeing white paper, you can see the question and the answer. Whoops. So there's the question. And there's the answer. Now, the next few questions here, 36 all the way through, let's see, I want to say 50 something. They deal with naming compounds and getting the formulas of compounds, which I'm going to actually cover tomorrow in lab. So we're going to skip these so that we don't duplicate our work on two days.
Okay.
And we're going to go to number 62. Okay. So
Okay.
36 through 60, you want to watch tomorrow's session or attend one. Fair enough?
Mm-hmm.
So let's go to 110. Calculate the mass in grams of the following. So we're getting close to the end of time, but today's session, not the end of time. I mean, it's not the rapture, Gabe, okay?
Solar flares are coming.
It could be the rapture. Just remember, if you're still here after the rapture, you suck. That's what they say, right? Okay. So here is the element gold. The number 79 is at the top, and the number 196.97 is at the bottom. This number here is the number of protons. This is the symbol. And this means that one gold atom has a mass of 196.97 atomic mass units. So we could say one gold atom is 196.97 atomic mass units of gold. Just like we could say, 16 ounces of bread is 1 pound of bread. Fair enough?
Mm-hmm.
Okay. Now it turns out that this also can be used as follows. It's a big jump, but 1 mole of gold atoms is 196.97 grams of gold. Same number, right? But different unit. What do we know about a gram compared to an atomic mass unit? And the answer is a gram is a whole lot bigger. In fact, one atomic mass unit is 1.66054 times 10 to the minus 24 grams. And whenever you have an equality like this, the smaller number goes with the bigger unit, always. I said smaller number goes with the bigger unit, right?
Mm-hmm.
Look at a foot and an inch. Which is the smaller number, 1 or 12?
1 is the smaller number.
Right. So which is the bigger unit?
The feet, I see.
The foot. Because the smaller number always goes with the bigger unit.
Okay.
Okay. So do you see how 1.66 times 10 to the minus 24 is really small compared to that?
Yeah.
So that means a gram is really big compared to that. So this bottom number means this, and this idea is called molar mass. And 1 mole of gold atoms is like saying 1 dozen gold atoms, but it's not 12. A mole is 6.022 times 10 to the 23. You want to memorize that number. So there's actually
A mole is always 6.022 times
That's
10 to the
right.
23rd.
Yeah. So doesn't it stand to reason that if you look at silver, which has the number 47 at the top, and at the bottom it has 107.87? So imagine each silver atom weighs less than a gold atom. Is that fair to say?
Yes.
Quite a bit less, right?
Yeah. Almost half.
Okay, so if we had 6.022 times 10 to the 23rd silver atoms, how much would that weigh compared to the gold atoms? And the answer is less, right?
Mm-hmm.
So it turns out that 1 mole of silver atoms is 107.87 grams of silver, which is less than 196. So that bottom number, instead of thinking about that being the atomic mass units of one atom, in chemistry, it's more useful to say, oh, that's how many grams there are if you have a mole of those atoms. And why do we use the term mole instead of 6.022 times 10 to the 23rd?
Easier to say.
Yeah, because 6.022 times 10 to the 23rd sounds like how much wood could a woodchuck chuck if woodchuck could chuck wood, right?
Yeah, except if it was about chemistry.
Yeah. So let's just say mole. There is an
Okay.
abbreviation for mole, and I hate it. It's MOL. I absolutely hate that abbreviation. I don't get it. Okay. So let's take a look at this problem here. What is the mass in grams of 4.24 moles of gold? And I'm going to put my solution, right in this box right here. So I'm going to put 4.24 mole of gold. Now, you see this conversion here that says 1 mole is 196.97 grams?
Mm-hmm.
Which side am I going to put in the bottom? The mole or the gram side?
The mole.
because we want them to cancel. Boom.
Mm-hmm.
What goes on top?
196.97.
Excellent.
So you multiply those two.
Now let's estimate the answer. We don't want to use 196. What's a simpler number to use?
200 or 195.
No. Can
Two-
you
two-
multiply something times 195 and figure it out? Or can you multiply something times 200 and figure it out easier?
200 way easier.
I'm going with 200. What's this number if you want to work with something?
So it'd be 200 times 4, 800.
800. So that's our ish.
Right.
Now, if
a
our
little less.
calculator spits out 8,250, guess what?
Hit the wrong button.
We hit the wrong button. Now, why do you think I'm always doing this?
Because you're human.
Because I didn't used to, and I used to put numbers down on the test that were ridiculous. And the teacher would like write a little note saying, Tony, you realize this answer is ridiculous. You came out with less than 1 atom. That's not possible. And I'd be like, oops. And 3 significant figures because of the 4.24. And this is the work I'd expect to see for a problem like A.
Okay.
How would we do B?
The same way?
Same way, but use the molar mass of,
Helium instead of gold.
there you go. And C, same way, but the molar mass of platinum.
Okay.
Now we'll do one more problem here. There's actually 4 parts, but if we do the first one, it's the same as the rest. So do you see now we're asked not to calculate grams, but to calculate moles? So sodium looks like this, 22.99 on the bottom. We have 16.0 grams of sodium. And this means that 1 mole of sodium is 22.99 grams of sodium. So what goes on the bottom?
22.99 grams of sodium.
Excellent, because that's what we want to cancel. What goes on the top?
1 mole of sodium.
What is the ish on our answer?
Less than 1.
Right. And I would say it's a little bit more than half. So to me, a little bit more than half is 0.6. That's the ish. How many zig figs?
3.
Right. So I get 0.696 mole of sodium. And I said 0.6, it's 0.69. Not bad. And you said more than half. It's more than half. Not bad. It's always nice to have an ish in your back pocket so that you feel a little bit confident about your answer. Fair enough?
Yeah.
So this is the work I would expect to see on a problem like this. And guess how we do the rest of these?
Same, but with
the correct molar mass.
Correct molar mass.
You got it. All right. Thank you for attending.
Yeah, thank you.
Appreciate it. And we will catch you hopefully tomorrow.
Sounds good. Have a good rest of your day.
You too.
Bye.
Bye-bye.